So you may remember from level two that you can classify alcohols. You may not, and because it wasn't very important in level two, but that's okay. So I'll go over it briefly. Basically, you can just classify an alcohol as primary, secondary, or tertiary based on how many other carbon atoms the carbon with the OH group attached to it is bonded to, which sounds confusing, but it's actually not. Basically, you just find the OH group and you look at the carbon that it's bonded to, and you just count how many other carbons that carbon's bonded to. So a primary alcohol would be like a straight chain alcohol like this one, where the carbon's bonded to one other. And then secondary, the OH group would be somewhere in the middle, and the carbon, if this you look, this carbon here is bonded to two other carbons. And then tertiary, a tertiary alcohol would have like side chains like this one, and the OH group, the carbon is bonded to three other carbons. It's not bonded to any other hydrogens. Um, Now, why does this matter? This is important because these alcohols form different products when they're oxidized. So one new functional group this year is aldehydes. These have the functional group COH. They got the double bond to the O and then an H on the end here. And these are formed by the oxidation of a primary alcohol. So you may remember last year as well that only primary alcohols could be oxidized to carboxylic acids. You could use an acidified oxidant like this one here, dichromate, or you could use MnO4 minus, but there's actually another step in between that. So here, a primary alcohol like ethanol, you could oxidize it with this acidified oxidant and it would actually form ethanal, which is the suffix for aldehydes, is anal. So it would actually form this before it would form the acid, ethanoic acid. So aldehydes also need to be separated by distillation when they're formed to prevent them from being further oxidized to carboxylic acids. And see this, like this example here, ethanol would be oxidized to ethanal, which if you kept oxidizing it would form ethanoic acid. Another new molecule this year is ketones, and these are formed in the same way as the aldehydes, using one of these acidified oxidants, Cr2O72 minus, or you could use MnO4 minus as well. But these are instead with a secondary alcohol, so an alcohol where the OH is somewhere in the middle, like this one here. And when you oxidize these ones, they're going to form ketones, so the double bond to the O is going to be in the middle here, and the carbon is bonded to two other carbons. So they have this functional group CO and then R and then this R. So the R's just mean any carbon chain length, and the dash just means it could be a different one. So basically the double bond to the O will be in the middle like this. And these are different to aldehydes as well because ketones they're not going to keep forming carboxylic acids. So you don't need to distill these to form them. You can just oxidize the alcohol without doing that. Because if you look at the carbon, it's bonded to two other carbons and it's already made four bonds because it's got the double bond to the O and it's got the single bonds on the side here. So it can't keep being oxidized because it can't form any new bonds to oxygen. It hasn't got enough space. And, because aldehydes, they can lose the hydrogen, but this carbon can't afford to lose any of these other bonds. So it's not going to form a carboxylic acid. So you can instead form these just heating under reflux, and then this will condense the vapors back down again. So for the properties of aldehydes and ketones, their boiling points are higher than respective alkane of the same length, because the C double bond O is very polar, because this O atom is very electronegative. It's going to pull all the electrons to itself, and this makes the bond polar. And so because the molecules are polar, they are held together by permanent dipole-dipole attraction. So they're going to have higher boiling points than alkanes, which just have the temporary dipole-dipole attraction. But their boiling points are lower than alcohols and acids because they don't have the hydrogen bonding from the OH group. So they're going to have lower boiling points than those. And small aldehydes and ketones are soluble in water up to 4 carbons long because of the polar C to O bond. But as they get above 4 carbons in the length, they're going to become less soluble. So, like 5 carbons, they'll become less soluble because the polar bond has less significance on the overall polarity. So it's going to decrease. If you had 2 unlabeled bottles of an aldehyde and a ketone, and that's a question that does come up a lot in NCEA exams as well. They love that question. If you had just an aldehyde and a ketone and you wanted to distinguish them from each other, one way you could do it is using an oxidant, because the aldehyde, if you remember, is going to keep being oxidized to form the carboxylic acid. So here you can see ethanol is going to form ethanoic acid. And then this is going to turn, if you use dichromate, it's going to turn from orange to green. So it'll start orange and then it'll turn green, and then you'll know that one's an aldehyde. If you use MnO4 minus, which you can use too, it's going to turn from purple to colorless. So just whichever one you find easier to remember, you can pick one of those. And always make sure it's acidified, needs to be. And another way you can distinguish them is using Tollens reagent. And that's basically got silver ions, which are going to be oxidized or reduced. Sorry, they're going to oxidize the aldehyde, and it's going to be reduced. So aldehydes will form a silver mirror because it will reduce the silver ions, and a ketone won't react. So basically, you can use either an oxidant or Tollens reagent, and the aldehyde will react, and you'll see a color change, but ketones won't react. And that's how you can tell them apart from one each other, because you see the color change.